I just realized there is a topic we should have covered when we did equations of a straight line in 2D, but we didn't. Maybe I didn't do it intentionally. Now, in 2D, we saw the standard form of the equation of a line. We also saw the slope-intercept form. Okay. What we did not cover is the parametric form of the equation of a line, and we will be using that a lot when we study 3D geometry. So I think we should quickly cover it in this video. Okay. Now, okay, this is the slope-intercept form, or even if you take the A standard form. Okay. If I say y is equal to t, okay, then x becomes t minus c upon m, okay, where t of course is a real number. Now I say, and I think, see, I'm not going to go into proofs, okay, I'm just going to demonstrate it and we are going to take it for granted and move on. Okay, I say that this is as much of an equation of this line as this one. Okay, let's quickly see how that works out. Now t can be any real number, so I am going to take several values of t and calculate x and y. Okay, let's say t is 0. If t is 0, y is 0, and okay, I'm going to take an actual line here, because we're not trying for a proof, yeah, so we just want to convince ourselves. So let's say I have a line 2x plus 3y is equal to 5, okay, and I rewrite this saying y is equal to t, so x is equal to 5 minus 3t upon 2, yeah, 2x, yeah, that's correct. Now I say this is as much of an equation of the line, same line as this one, okay. So if t is 0, y is 0, and if t is 0, then x is 5 by 2. Let's take another point. Now what I like about this format, or this form of equation of a straight line, and you have to assume, you have to take my word for it that this is the equation of the line, that this is some kind of a machine to generate points on the line. So I take t is equal to 1 and y is equal to 1 and x is equal to 5 minus 3 upon 2, which is 1. If I take t is equal to 2, then y is equal to 2, and this is 5 minus 6 upon 2, which is minus 1 upon 2, and you can go on generating these points. Now the first thing is, so the points we have are 5 by 2, 0, 1, 1, minus half, 2. So these points obviously satisfy these equations, that is, these points lie on whatever this represents, and since we have just restated this, these points will satisfy this equation too, but let's check anyways. Okay, let's look at the first point. 2, 5 by 2 plus 3 into 0 is equal to 5, which is the right hand side. Take 1, 1, okay, 2 to 1 plus 3 into 1, obviously this is equal to 5, satisfies this equation. 2 into minus half plus 3 into 2 is equal to minus 1 plus 6 equal to 5, satisfies the equation. Obviously it was going to, so please understand that. Okay, so is there a general form for the parametric equation of a line? Yes, I think y is equal to k1t plus k2 and x is equal to k3t plus k4, where k1, k2, k3, k4 are real numbers, I think this should just about give us any line if you do the variations of. The important thing is x and y to be represented using expressions which are the first power of a parameter, which is t, right? I'm using t, so you can't go t square, you can't go t cube, you can't go root t, etc., etc., etc. So the first power of t. So this is the parametric equation of a straight line, and given any equation, you can quickly convert that into this. Now, why is this important? Okay, this is important because when you go to 3D, and I briefly mentioned, I think in an earlier video, or if not, it will come up in future videos anyways. Okay, ax plus by plus c equal to d is the equation of a straight line in 2D, right? One is tempted to believe that ax plus by plus cz equal to d would be the equation of a straight line in 3D. One would just like to extend. Not true. Okay, this in fact in 3D is the equation of a plane in 3D. Well, if this is the equation of a plane in 3D, then what is the equation of a line? Because we have lines in 3D too. The only way I know to represent a line as equations or equation in 3D is the parametric form. So x is equal to k1t plus k2, y is equal to k2t plus k3t plus k4, z is equal to k5t plus k6, where k1, k2 up to k6 are elements of the set of real numbers. This is the way I know to represent a straight line in 3D. Now please understand, I have not researched this topic much. I've just learnt it as I went along, experimenting with linear algebra. But I believe this is the only way to represent a straight line in 3D. Now let's demonstrate this to ourselves. Again, please understand, these are not proofs. We are just doing one-off demonstrations. Maybe someday I'll try to figure out proofs, and then I'll make a video out of them. But for now, we are just going to try and demonstrate this to ourselves. While doing that, we may have some fun and practice with vectors. Now let's say I have a plane. So we are assuming this is a plane. I'm just going to go ahead and assume that this is the equation of a plane in 3D. Yeah? Okay. Now I'm going to find out 3 points on this plane. I'm getting a bit confused about what I am trying to do. This is not what I am trying to do. I am trying to prove or demonstrate to us that something like x equal to k1t plus k2 and so on and so forth can represent a line in 3D. Yeah, okay, sorry, I got my bearings now. So let's say I have x equal to t plus 1, y is equal to 2t minus 3, and z is equal to t, and I claim that this represents a straight line in 3D. Okay, let's see at least for one line. Okay, so we'll do the same thing again. Okay, various values of t, and we calculate x, y, z. Okay, so t is equal to 0. What does that give me for x? It gives me 1 here. T equal to 0 gives me minus 3. T is equal to 0 gives me 0 here. T equal to 1. Okay, so t equal to 1 gives me 2. T is equal to 1 gives me minus 1, and t is equal to 1 gives me a 1 here, and I'll take t is equal to 2. Okay, 3, 1 and 2. Let me double check. minus 3, 0, 0, 1, 2, 1, minus 1, 1, 3, t is equal to 2 gives me a 3 here, 1, yes. I'm just improvising, I'm not really prepared for this video, so, bear with me. So what we really got was, we got 3 points now, and we want to make sure that they lie on a line. Now, if this were 2D and we had 3 points, I would just calculate the slope using xy, these 2 points, the slope calculating using these 2 points, and if the slopes were equal, I would conclude that these 3 points lie on the same line. I don't know how to do that in 3D. I don't know how to calculate a slope in 3D. So I'm going to try something else, right? Let's draw our 3D plane. Okay. X, Y, Z. Okay. So these 3 points belong to the XYZ plane, and we want to check whether they all lie on a single line. Okay. Now, let's say this is a line in the XYZ plane. Okay, you got to use your imagination a bit. It's hanging somewhere, in thin air. And let's say we have 3 points. Okay, points, vectors, right? 1, minus 3, 0 in the coordinate plane is really a vector 1, minus 3, 0, right? So now we are going to talk vectors. So let's say this is my point, this is the other point, this is the third point, and let's call them vectors A, B, C. Okay, now if you remember A minus B, right? If you remember the head to tail positioning, then A minus B is really, let me get some colored pens here. So A minus B is this vector right here, right? From the head of B to the head of A, that's A minus B. B minus C is this vector, and A minus C is the vector all the way from here to here. A minus C. If I can find the values of A minus B, B minus C, A minus C, and see that they are all collinear, then I think we are there. So let's say, A is this point, the vector represented by this point, 1, minus 3, 0. B is this point, 2, minus 1, 1. And C is the third point, 3, 1, 2. Okay, 1 minus 3, 0, 2 minus 1, 1, 3, 1, 2. Okay, so I am going to find A minus B. Vector subtraction, simple, right? A minus B is equal to 1 minus 3, 0, minus 2 minus 1, 1, which equals 1 minus of 2, minus 1, minus 3 minus of minus 1, minus 2, 0 minus of 1, which is minus 1. Okay, very good. B minus C equals 2 minus 1, 1, minus 3, 1, 2 equals 2 minus 3, minus 1, minus 1, minus 1, minus 2, 1 minus of 2 minus 1. Check this out. A minus C equals 1 minus 3, 0, minus 3, 1, 2 is equal to 1 minus of 3, which is minus 2, minus 3, minus 1, minus 4, 0, minus 2, minus 2. Okay, look at this. I think we spent enough time discussing collinear vectors, right? So what you really have is, and I think this is obvious to you by now, but I'll just rub it in. Okay, we have a first vector a minus b, which is equal to 1 minus 2 minus 1. We have b minus c, which is equal to this 1 minus 2 minus 1, and we have a minus c, which I'll just take 2 out, and you have 2 minus 1 minus 2 minus 1. So I think it's very obvious that these are scalar multiples. In fact, these two are the same vectors, and since they are scalar multiples, they lie along the same line, right? So first we convinced ourselves that 3 points on the same line give us vectors whose subtractions are along the line. Then we took these three and concluded that since they are scalar multiples of each other, they are collinear and hence lie along the same line, and hence, at least in this case, we are certain that this represents the parametric equation of a straight line. Parametric equation of a straight line in 3D. Maybe I can do a proof later if I can figure it out, but for now I think we have enough background to know or to recognize the equation of a straight line when in 3D when we come across it, and this will be very important when we do matrix elimination equations, matrix elimination exercises for 3D equations. Let's stop here. I hope that was clear. But some practice, if you do some practice on your own, it will help you better.